Hello, I'm Mohit Sharma. I am a third year undergraduate in the Department of Physics at IIT Roorkee, and today I'm going to be implementing a program to calculate the Hamming distance between two numbers on an 8085 microprocessor. So I'll begin by defining what a Hamming distance is. So Hamming distance between any two bit strings, which I'll assume to be of equal bit length here, is the number of positions at which they have different bit values. So for example, looking at the two inputs A and B in this diagram here, if we start iterating from the least significant bit towards the most significant bit, we'll see that the second, fourth and third last positions are the only positions where they have different bit values. Therefore, the Hamming distance between these two inputs here would be 3. So why would I need to calculate the Hamming distance between two bit strings? So Hamming distance actually sees a large number of applications in coding theory and cryptography. Most notably, it's used in error measurement and correction for in coding theory, and in cryptography it's used for the statistical cryptanalysis of a number of popular crypto systems, for example as demonstrated here in this CryptoPals challenge. That being said, I'll now move on to the actual implementation, for which I'll be moving on to my handy 8085 GNU simulator. We'll look at two approaches, a simple brute force approach and then a slightly optimized version of it. So this right here is a simple brute force approach to calculating the Hamming distance between two 8-bit numbers. So in order to understand how the algorithm works, what we're going to do is we're going to step through the code line by line using the debugger that GNU simulator provides and examine the registers and stack at each point to understand how it works. And I also have a small Python script here which calculates the Hamming distance between two numbers so we can verify our results later on. So starting out, the inputs are stored in the B register and D register. The counter is initialized with a value of 8 because we have 8 bits to iterate through. And the actual value of the Hamming distance is going to be stored in the register H, so we initialize it with 0. Then we simply initialize the stack pointer and jump into the loop. So inside the loop, what happens is, I move B into the accumulator and then I push it onto the stack because we're going to need it later. And then I AND it with 0, 1, and what this does is it masks out all the bits in B and all the bits in accumulator instead of the least significant bit. And then we move this value back into B. So B now holds the least significant bit of its original value, and the original value is pushed onto the stack so we can retrieve it later. Then we kind of do the same thing with D, except we don't move the least significant bit back into D. Instead we keep it in the accumulator and subtract B from it. So because at this point B holds the least significant bit of its original value, this subtraction instruction would result in 0 if B and D had the same bit in that position, and it would not result in 0 if they had a different bit. So if they didn't have a different bit, then we are going to increment the Hamming distance. So if that's the case, we jump to this portion here which increments H by 1 and then jumps back where we left off. At this point what we do is we move the original value of D into the accumulator and then we rotate it and then we move it back into D. So what this does is it gets rid of the least significant bit and it gets rid of the least significant bit, and the second least significant bit is now at the first position. So using this we can iterate through all 8 bits. Then we retrieve B from the register and do the same for it, and then the loop continues for all 8 bits, and by the time it ends the H register should hold the value which signifies the Hamming distance between our two inputs. As you can see, H here holds 5. We're going to use the Python script to verify if this result is correct, and indeed it is. So as mentioned in the beginning, this was a brute force approach, and admittedly it's rather inefficient. The loop itself is 16 instructions long and it's executed 8 times. So can we optimize this further? It turns out that we can, because one way to think about Hamming distance is, since it only tells us the number of positions at which both the inputs hold different bits, then this can be optimized using an exclusive OR operation. So if I XOR two inputs, then essentially the resultant value will have a value of 1 wherever they had wherever they held different bits, and a value of 0 wherever they held the same bit value. So I can so if I want to calculate the Hamming distance between two numbers, what I can do is I can count the number of ones in the binary representation of their XOR value. So this here is the optimized approach, and right off the bat we can notice that it's significantly shorter and as a result much more efficient than the first program. It's pretty simple to understand. So the way it works is the same as before. We move both our inputs into the B and D registers. We initialize the counter with a value of 8, and our Hamming distance is going to be stored in the register E. I move B into the accumulator and then XOR it with D. And now I simply need to count the number of ones in the accumulator. And the way I do this is I rotate the accumulator without carry, and if it results in a carry, it means that the least significant bit was 1. In which case we need to increment E by 1. Otherwise we skip this instruction and move to the next instruction, which simply decrements the counter and continues the loop. And by the end of this iteration, we should have the Hamming distance between the two inputs in E. And as we can see, E now holds a value of 0.5, which, as we verified earlier, is the correct Hamming distance between 1, 7 and 9, 8. And that will be about it from my side. Thank you.